What happens in odd and even? We already mentioned this. You can predict the membership in one based on the membership in the other. And if we draw it in a two-set Venn diagram, if I call this odd and I call this even, what numbers are both odd and even? Nothing. So you leave this space blank. What numbers are odd but not even? 1, 3, 5, 7, 9. What numbers are even but not odd? 0, 2, 4, 6, 8. What numbers are neither even nor odd? There's also none there, so that's also blank. The intersection is blank. The outside of the union, empty. The outside of the union is also empty. So when this happens, there's no need to draw a general two-set Venn diagram with 4 segments and then mark 2 of them empty. There's an alternative. You can just draw a one-set Venn diagram, and that circle can be named either odd or even, doesn't matter. If I name it odd, what's inside will be the odd numbers, and what's outside will be the complement of the odd numbers, which will be the even numbers. 0, 2, 4, 6, 8 will be outside, and 1, 3, 5, 7, 9 will be inside. You can reduce the number of sets that you have to draw. And this is always advantageous. You will see that when you do the DI sets based on Venn diagrams. And I can demonstrate this right after we do the next example. We have seen this example already. I am partitioning the set into 3 subsets based on what is the remainder when you divide the element with 3. The remainder can be either 0 or 1 or 2. That is why we have the 3 sets. And these are the elements in each of these sets. What will happen if we draw a 3-set Venn diagram for this? Here we have a general 3-set Venn diagram. I have my R0, R1, R2. Are there any numbers which give a remainder of 0 and a remainder of 2 when you divide it by 3? Not possible. You cannot have more than one remainder. So R0 intersection R1 is empty. R1 intersection R2 is empty. R0 intersection R3 is empty. And the numbers that leave a remainder of 0 will go here. 0, 3, 6, 9. Remainder of 1, 1, 4, 7 will go here. And the remainder of 2 is given by numbers 2, 5, 8. They'll go there. And do we have a remainder other than 0, 1, 2? We don't. So the outside of the union is also empty. So you notice that 5 of the 8 segments in the general 3-set Venn diagram are empty. And so we don't need this kind of a diagram here. It's inefficient. What can we do instead? We can just put 2 disjoint sets. We know that these are mutually exclusive and collectively exhaustive. What we have here is a MEC, 3 sets which are MEC. The previous example were 2 sets which are MEC. If you have or a binary partition, that was the previous example. And this, if you want, you can call it a ternary partition. If you have a binary partition, then one is the complement of the other. So we had one set. Here we have a ternary partition. R0, R1, R2 are disjoint. So there's no intersection. You can simply call one of them R0 and one of them R1. And the region outside both the circles will represent R2. So you can just put 0, 3, 6, 9 here, 1, 4, 7 here, and 2, 5, 8 is outside the union. The union is basically the entire region inside the 2 circles, and that will correspond to the 3rd set. So what you'll notice is that when you have partitions, you need let's say x minus 1 sets for an X set partition. 2 set partition required only one circle. Inside and outside you had 2 regions. 3 set partition required 2 circles. Inside one, inside the other, outside both. So the more efficient way of drawing 3 sets, if they happen to be a 3 set partition, would be this. Don't draw a general 3-set Venn diagram with 8 regions. Just draw 2 disjoint circles, which will give you a total of 3 regions. Now, what if I had to show all of this information, these last two examples, odd, even, R0, R1, R2, if I had to show all of them simultaneously in one Venn diagram, what do I do? Now, without the optimizations that we just mentioned, you have 5 sets and you need to draw a 5 set Venn diagram. And you can't draw a 5 set Venn diagram with the 32 regions. So that's not feasible. But with the optimizations we mentioned right now, I have one set for the binary partition, odd versus even, and I have two sets for the ternary partition, remainder of 0 versus 1 versus 2. And so we can actually draw this using 1 plus 2 3 set Venn diagram. Let's see what that looks like. This is the Venn diagram that I would use. Notice that this is not a general 3 set Venn diagram with 8 regions. This actually has only 6 regions, and that's because my R0 and R1 do not need to intersect. Their intersection is null. So I've removed two regions from the general 3 set Venn diagram that are going to be empty anyways, and I've drawn a simplified diagram with R0 and R1 disjoint. But that was 2 of the 3 sets in a ternary partition. You had a separate partition which is based on odd versus even, and I can take the same odd set that I took in the previous diagram, and this odd set has to intersect with both R0 and R1. So then your 6 regions are basically R0 intersection even, R0 intersection odd, R1 intersection even, R1 intersection odd, R2 intersection odd, R2 intersection even. And so if you were to fill up, if you were to place these 10 elements in this Venn diagram to show what these set relations look like, what I would do is I'll take all the odd numbers, which are 1, 3, 5, 7, 9. And then out of the odd numbers, I look at what is the remainder when you divide by 3. 3 and 9 give a remainder of 0. So these are in the intersection of R0, O. R0 means remainder of 0 when you divide by 3. O means odd. Odd numbers which divide by 3 and give a remainder of 0. The numbers are 3 and 9. Then what about 1 and 7? 1 and 7 are odd numbers which leave a remainder of 1. 1 and 7. 5 is an odd number which leaves a remainder of 2. So that 5 will go here. Then you have your even numbers which are outside the O circle. You have 0, 2, 4, 6, 8. 0 and 6 leave a remainder of 0 with the divisor 3. Outside O, R0. So basically R0 even would be 0 and 6. 2 and 8 leave a remainder of 2. R2 even would be 2 and 8. And then 4 leaves a remainder of 1. That will be even number with a remainder of 1 when you divide by 3. That 4 will go here. Notice that if you had not applied the simplifications, you would need a 5 set Venn diagram and it wouldn't be feasible. And so we must always try to find the least number of sets we can draw in a Venn diagram that will make the solution to, for example, a DI puzzle, a DI or an LR set from Venn diagrams will be easier the less number of circles you draw. And so we must always strive to do that. And they just demonstrate that you need only, this is an example that demonstrates a situation where you need only 3 sets where it initially shows you 5 sets.